Make sure you have read the chapter before you begin this video. Entropy is a measure of how many possible states the system can be in. When muscles are used to lift something, they do this because there is an increase in entropy at the molecular level, where ATP becomes ADP and inorganic phosphate. This is an increase in the number of molecules, which in turn has more potential states in which to exist than a single molecule does. Let's look at some chemical changes and see if we can decide whether they represent an increase or decrease in the total entropy of a system. First, we have gas condensing into a liquid. From our time studying intermolecular forces, we know that liquid molecules are more restrained than gas molecules, so the entropy would go down in this situation. What happens if we heat a gas from a lower temperature to a higher temperature? Higher temperature molecules have kinetic energy, and thus have more possible states in which they can exist. The entropy would go up in this situation. What about this chemical reaction? The number of moles decreases when product is formed. Less molecules means less possible states, thus the entropy goes down. The opposite would also be true. We can recognize this as a state change. Because we are going from a liquid to a gas, we know that gas can have more possible states, and thus entropy would go up as this reaction proceeds. Just like enthalpy, entropy is a state function. We can calculate entropy using standard entropies, as we did with enthalpy. Let's do one. Here we have oxygen gas and hydrogen gas combining to make water. We would predict a decrease in entropy based on the number of moles being reduced on the product side. Let's see what we get. We add up all the standard entropies of this reaction and subtract the reactants from the products. We get negative 88.5 joules per Kelvin, a decrease as we expected. Let's try this with our state change equation. We simply look up the standard entropy values for each compound. Then we subtract the reactants from the products. For this state change, we get an entropy change of 118.92 joules per Kelvin. This is an increase in entropy as we have predicted. Anytime we are calculating a state change, we can use our enthalpy value for a state change and the entropy equation for a reversible reaction. This is really the only situation we will be using this equation in. For our boiling water example, we can calculate the enthalpy using the heat of formation values. Then we divide that by the temperature in Kelvin, and we get 118 joules per Kelvin. We can use Gibbs free energy to determine whether a reaction is spontaneous or non-spontaneous. We can use the equation for Gibbs free energy, where free energy equals the enthalpy change minus the entropy change times the temperature. For this reaction, where two oxygen atoms combine to make O2 gas, we would predict that the enthalpy would be less than zero because we are forming a bond and not breaking any. We also would assume that entropy would go down because we have less moles of gas on the product side. Let's do the full calculations now and see what we get. For enthalpy, we subtract the reactants from the products using our standard values, and we get negative 494 kilojoules. For entropy, we can do the same for the standard entropy values, and we get negative 117 joules per Kelvin. Now, we put those into our Gibbs free energy equation, where the free energy equals the enthalpy change minus the change in entropy times the temperature in Kelvin. We get minus 459 kilojoules, so the reaction is spontaneous. We can also use this information to calculate the temperature where this reaction would switch from spontaneous to non-spontaneous. We can set the free energy equal to 0 and arrange the equation so that temperature equals the enthalpy change over the entropy change. We get 4,220 Kelvin. So the reaction below this is spontaneous and above it is not. For standard conditions, we can use a table to calculate Gibbs free energy values in the same way we do for enthalpy and entropy. For this reaction, we can look up the free energy values and simply add up the values for each side of the reaction, and subtract the reactants from the product. Easy, we get negative 130.19 kilojoules. For Gibbs free energy in non-standard conditions, we'll be using this equation to calculate free energy. The non-standard conditions free energy value is equal to the standard free energy plus the gas constant times the temperature times the natural log of the equilibrium constant Q. Consider this reaction. We can calculate the standard free energy needed for our equation using the table of values. We subtract the reactants from the products and we get negative 1,109 kilojoules. We can then determine if this reaction will be spontaneous in non-standard conditions at 298 Kelvin with these concentrations. First, we calculate Q. It's important to include the exponents on the concentrations based on the stoichiometry of the original equation. Remember that Q is not necessarily calculated using the concentrations at equilibrium. We then plug this value into our equation. We need to use the appropriate gas constant and then convert that to kilojoules so we can add it to the kilojoules from the standard free energy we calculated earlier. We put all this into the equation and we get negative 1,075 kilojoules. This reaction is spontaneous at 298 Kelvin.